for me already, in the sense that I think with these optical techniques, they're extremely sensitive in some specific cases. And of course, some other techniques are better for, say, larger molecules or more volatile gases. And perhaps the arc of my presentation here can end in the idea that if we all work to our strengths, but also work on kind of miniaturizing and ruggedizing our different techniques so that we can combine them into single devices that actually span all of the contaminants that need testing, as we're looking for how we make gas sensors in the future for all sorts of applications. So this talk is specifically about optical gas sensing. I'm at NPL with a number of colleagues who you have heard from and will hear from today. NPL is the UK's National Metrology Institute, if you're not familiar with it. We have a large number of research groups across all types of metrology that you could be doing in a science institute. This allows us to really gather expertise across a number of fields and sectors. And specifically in the NPL talks you'll be hearing today, you'll really see how the combination of having an optical metrology group and also a gas metrology group allows us to create the kind of sensors that can be calibrated and used throughout different industries. Just to kind of set you up for my talk as an overview, first I'll motivate this. We've heard this from a lot of the other speakers already, but I'll just remotivate. Then I'm going to specifically give you details on an extremely advanced and sensitive optical detection technique called Nisomes. And then I'll kind of finish off by looking ahead to what are the next steps in improving and making more sensitive optical detection techniques in both kind of industrial clean room settings and in others. So the application sensors, obviously, there's a big focus on clean room techniques here. And so for industrial detection, it's across a number of fields, but it's really about how do we mitigate these adverse effects on the kind of production line when you have contamination of different kinds. And we've talked about a number of different AMCs that we're interested in detecting at better and better sensitivities as the processes become tighter. There's also a lot of application for trace gas detection in the environmental sector, whether you're trying to look at clean energy and fuels and looking at contamination within, say, biofuels and hydrogen fuels. This is actually a picture here. NPL has a hydrogen refueling station, and they do metrology on the hydrogen gas used for that. But also for greenhouse gas monitoring and also source tracking, so needing extremely sensitive detection of different isotopologues of the same molecule. There's a push to medical applications for gas sensing, especially in exhaled breath. And a lot of the same contaminants that we're worried about in industrial settings are the ones that you need to be able to detect for both environmental and medical use. So in kind of trace gas detection, there's 4 really important pillars that we need to address. One is the selectivity. Are we able to know which molecule we're seeing, or do we just detect contamination in general? How sensitive can this be? The speed at which you can do detection. Some of the earlier talks focused on how long a time it can take to collect enough gas to do measurements. What we're really looking for in these industries is real-time or online sensing. And then from a metrological point of view, can we calibrate our detection? In some applications, you need to know exactly how much of the contaminant you're detecting. Although in some applications, it's only, all you need to know is that contaminant present. So really, as a general motivation for very sensitive optical trace gas detection, there's just a need across all these sectors for real-time calibrated measurements of these different contaminant gases. Nisomes is an extremely complicated technique in optical sensing. It's kind of a culmination of a number of optical techniques put together, some of which have been described in detail in previous talks, but I'll kind of motivate it as a as a description through the acronym of Nisomes, which stands for Noise Immune Cavity Enhanced Optical Heterodyne Molecular Spectroscopy. And I will walk you through that in the talk. But first, I want to say the first demonstration of this was actually back in 1998 by Junyi, Longshen Ma, and Jan Hall at Gila in Colorado. They were looking for really sensitive detection of, it was acetylene and carbon dioxide molecules, more from a metrological point of view than a contaminant gas point of view. But just to give you an idea, they demonstrated a detection sensitivity that, to put it in perspective for, say, ammonia detection in the near IR, so as some of you know, quite far from the strongest lines, it's a sub-PPT detection at 1 second. Now, there really isn't any real-world applicable device that can do this now. So what were they able to do in their laboratory setting, and why were they able to create such a sensitive device? And it boils down to 3 things. One is they had an extremely narrow line width and stable laser. The second is they had an extremely long and extremely high finesse cavity. And I'll describe why those things are important in Nisomes and why some of them aren't really practical for the kind of real world online detection systems that we would all like to produce, but how can we work towards that in a real system? So to start, Nisomes is based on molecular spectroscopy. It's absorption spectroscopy. And to start us all in the same place, you have a laser that is passing through a sample of atoms or molecules, N of them, and it hits a detector, and the sample length is considered a length L. By this Beer-Lambert law, you can talk about the linear absorbance over a path length L, which consists of the number of molecules, this interaction path length, and the cross-section sigma. So sigma is slightly more complicated. There's, you can usually look at it in terms of a line intensity. These line intensities for many, many molecules are compiled in different databases. HyTran is one of our favorites. But the cross-section in reality also has an absorption profile, which can be calculated. We can look at this in real time by observing the transmission of light through our sample. So taking information from the HyTran database and looking at ammonia, which was the first contaminant our Nisome system was focusing on, you can see that at very low wave numbers, or if you're more a wavelength kind of person, around 10 microns, you have the strongest line intensity for ammonia molecules. There's a number of other bands of excitation, some down a few orders of magnitude in strength at the kind of 2 to 2.5 micron range. And then in what I would consider as an optical metrologist, the telecom range at about 1.5 microns, you also have some lines. Now we're interested in the telecom range simply because it's telecom, there are a lot of commercially available devices that we need to be able to perform Nisome spectroscopy, specifically frequency modulators. And because it's telecom, they're also fiber coupled. There are also lots of lasers and narrow line width lasers produced at the telecom range. So instead of having to build and create all of the components of our systems in a bespoke manner, we're able to create a kind of plug and play fiber optic connected system from the get-go, as long as we're willing to take the hit in line intensity by working in this very near IR regime. However, the sensitivity can be greatly enhanced by, of course, enclosing your atoms in a cavity, as has been talked about previously. So instead of our length L, we now enclose our sample with some cavity mirrors. There are some descriptions of cavities previously, but what you really should know is there are certain resonant frequencies that are allowed to build up in a cavity, and it has to do with the length of the cavity. So you get a mode spacing of different frequencies that your laser can input that will be allowed to build up and also leak out of these cavities, as much in the same way as with the cavity ring Dohn spectrometers. And the key points to think about are the cavity finesse, which is of course related to the reflectivity of the mirrors. The enhancement factor goes here in terms of the finesse of your system. So instead of the length, you now have this effective length. So for the kinds of cavities we're designing for Nisomes, our cavity finesse is about 170,000, which takes a 10 centimeter cavity length and turns it into a nearly 11 kilometer cavity length. So it's an enormous enhancement factor, which allows us to work in the near IR and still have incredible sensitivity to these molecular lines. The pictures down here are the real cavity that we used for our ammonia system. You have a piezo stack holding a very high reflectivity mirror. We have an open cavity, which is very different than for the cavities that you use for laser stabilization and other fields, which would be as solid a device as possible. But of course, for trying to flow gas through this cavity for real-time measurements, we have to compromise on the stability of the cavity itself. So what are some challenges of having these very high reflectivity mirrors and high finesse cavities? Getting the kind of high reflectivity you need to have these kind of effective lengths that we're looking for Nisomes, you really need to be working in the near IR. It's only very recently that cavity mirrors can have high reflectivity above 2 microns. But now, even in the past few years, these have become commercially available. They're not just bespoke items that are used for gravity wave detectors, for example, or very bespoke optical frequency metrology at the kind of national metrology lab level. Another point of having a very high finesse cavity is you get a very narrow line width of the cavity. What that means in practice is if your laser line width is broader than that, then you're losing power. And in fact, if the laser frequency is jittering around, then the noise of that frequency actually on the detector looks like amplitude modulation noise. And so if you're trying to couple a noisy laser to a narrow cavity, and then you're also hampered by the fact that it's not a completely stable system because it's open and gas is flowing through it. These are additional noise sources for this type of device. So the power of the Nisomes is, of course, in its noise immune capabilities. And that initial bit of noise immunity that I'll talk about is getting rid of this laser noise. So the idea is that if you scan your laser frequency, there are these and then you look at the cavity transmission. As I said before, there's certain resonant frequencies that will be allowed to propagate in the cavity, and if you're off that frequency, no light will come out of your cavity. What we do for Nisomes is we put a frequency modulation on the laser, which creates sidebands. So here's the carrier. This is the frequency your laser is at. The frequency modulation puts sidebands on that, and we tune the sideband frequency so it's equal to this free spectral range. Now, that allows both the carrier and these sidebands to transmit through the cavity, through our sample of atoms. Now, it doesn't solve the FM to AM conversion problem, but the sidebands and the cavity, the initial cavity frequency, the initial coupled laser frequency will all move up and down in amplitude together. And that therefore the detection system that you knew that you're using, it's really this relative interaction of the size of the sidebands to the size of the carrier that gives you the spectroscopic signal. And it's the fact that when your molecules are interacting with one of these three triplets, one of these three laser frequencies, it will adjust how the output on the detector is when we demodulate the system on a double balance mixer, which is this optical heterodyne technique. So if there's no interaction with a molecule, the interaction between these three frequencies will just beat and give you a 0. Whereas if one of them changes in size due to some interaction with a molecular sample, then you get a non-zero output, and that is your signal for the Nisomes system. I'll just very briefly show you, it's quite a it's quite a complicated system to put together in terms of the number of electronics and laser stabilization and frequency modulation components in an Nisome system. But just very briefly, you have your initial laser. We use a fiber coupled DFB laser that comes out single frequency. We then have a fiber-based electro-optical modulator, which puts the sideband frequencies on it. We have a low-frequency modulation at about 15 megahertz that just allows us to do standard Pound-Reaver-Hall stabilization to lock the laser to the cavity. Then we have a second oscillator, which is approximately at the free spectral range frequency of our 10 centimeter cavity, which is about 1.5 gigahertz, and that allows us to create these sidebands for the Nisome signal. One of the important things is that you maintain this relation between the sideband frequency and the actual free spectral range of the cavity, and we use another type of laser stabilization lock to feed back to this oscillator frequency to keep our sidebands on resonance with the free spectral range. And we can see that, I don't know if you can see this picture here, if it's too small, but if you're looking at the transmission of light through the cavity, it goes through a little peak maximum when not only the carrier, but also the sidebands of your laser all pass through the cavity simultaneously. And we can stabilize to that point when we do our Nisome spectroscopy. The final output signal, when it's demodulated, as you scan the frequency through, this is actually a double peaked ammonia feature at 1531 nanometers. You get this kind of dispersion feature, and that allows you to, you to get an estimate of the amount of gas in your sample. So the way this is a sample, it doesn't give you an absolute measurement of your sample, but it does allow you to calibrate your system to an absolute. So we were able to use a dynamic dilution device developed by the gas metrology group at NPL. And for example, we took, this is a 5 micromole per mole sample, so 5 ppm sample of ammonia in dry nitrogen. You can look at the transmission at this, it's quite a high absorption because it's quite a high concentration given the effective path length that our laser is going through. But if we also we were able to get a sample at, say, 230 nanomoles per molar, 230 ppb, and down to about 150 ppb, you can see that the transmission isn't nearly as great, but you still have a very definitive Nisome signal. We were able to then calibrate our Nisome system. And so therefore, if we were to take another gas at an unknown concentration and measure the amplitude of the signal, we would be able to use this device as an actual measurement device. I should also note that you can add an extra layer of wavelength modulation to the system, and instead of having 0 crossings and having to fit an entire feature, you would actually just have a value at the maximum in your spectrum. And so you could have a much simpler calibration in a working system. This was published a number of years ago and was part of the work initially done under Metrology for Airborne Molecular Contaminant grant, where we were looking at a detection for ammonia at 100 nanomoles per mole in 5 minutes. And of course, now in this kind of second follow-on funding for META-AMC2, we're looking at HCl and also on our device, water vapor, with a detection requirement of 1 nanomole per mole in 1 minute. And that's the system we're building up now in-house. So this is an extremely sensitive way of detecting at least ammonia and hopefully HCl as we go on. But what are we looking for in the future of optical sensing? Well, considering how well many of commercial systems can already perform, we need to find our niche. And as Jens was saying, in his system, very, VOCs and very complicated molecules, that's ideal for that kind of device. And so we're really focusing on much simpler molecules, but how would we be able to extend this in optical sensing to more complex molecules? How do we deal with co-contaminants? If you're trying to do gas sensing in methane fuel, how do you deal with the really strong methane signal? How do we increase our sensitivity and speed of detection? How do we create devices that allow multi-species detection in one device, so we don't have to have a bespoke Nisomes system for ammonia and one also for HCl? It's difficult to get mirror coatings that in a single cavity would be able to cover the entire spectrum we're looking for. Can we move into the mid-IR with these systems? Can we improve upon the technology? Will the commercial modulators and lasers be narrow enough that allow us to get into the mid-IR and make Nisome systems there? And also, as we move into new sectors, there are going to be new challenges outside of the clean room. How do we bring a breath analysis system into a hospital setting? How do we create an inline detector for a hydrogen fueling station? One very basic thing we're doing already is in this next MetaMC2 project is we did have mirror coatings made for our cavity that allow us to detect HCl and water vapor concentrations using the same system. But it does take two lasers incident on the same cavity to do that. NPL has a long history and high level of expertise in cavity design and laser stabilization. What I've shown here is an example of a cubic cavity. It has up to 3 axes, which you could have mirrors that have various coatings. So you could do 3 or more different contaminants using the same cavity system. It's also intended for use in space. So it's very rugged. I don't think there's anything on Earth that's as crazy as trying to put something into space. And so it's already been designed to be very robust under vibrations, under inversion. And lasers, you can create laser systems that remain locked to this, even in really, really rugged conditions. But what would be kind of a big step change in the optical detection of gases? Well, a big one, in my opinion, would be in dual comb spectroscopy. So that's using an optical frequency comb system. That's a pulse laser system. If you're not familiar with them, it's essentially a pulse laser. So the output comes out as pulses in time, and the spacing between those pulses is what I'll call 1 over the repetition rate. And what you get, though, in frequency space, if you looked on an optical frequency detector, is a comb of laser lines, essentially. And they're all spaced by this repetition rate. This has a lot of applications in frequency metrology, because you can connect the SI microwave second to optical, into the optical domain and precisely measure the frequency of all these. So that gives you a way to calibrate systems that use this for measurement. But one of the things you can do with combs is do molecular spectroscopy. And here's a really excellent review article if you want to get started in this field. But the idea is you take multiple combs and kind of shine them through each other, and the resultant beat that you get allows you to detect molecules much in the same way as a standard heterodyne laser interferometry system like a Nisome system, but using these frequency combs. And the power here, if it isn't completely obvious, is that this comb of frequencies can even be octave spanning. So it can be a full optical octave of wavelengths. So you're not just thinking about, oh, how do I look at one single molecule? You can now look at a whole spectrum from, 1.5 microns to 2 microns, or even into the mid-IR. These combs span into the mid-IR now. And as a even more future view, the future of frequency combs is in microcomb technology. And these are fabricated micro resonators that create a comb-like structure in the same way as these optical frequency combs. What's so powerful about them is because they're fabricated device, you can integrate them, they're obviously very small, you can integrate them into more complex systems, and they have applications in far more than just gas metrology. And so the technology is being pushed in all sorts of directions. Um, Once you're doing optical frequency comb spectroscopy, you can cavity enhance this as well. And that, of course, increases the sensitivity. So even if you were still in the near IR regime, you could increase the sensitivity of your device. To do that, of course, much in the same way as in Nisomes, you just have to match this repetition rate of your laser to this free spectral range of your cavity. And then all of the modes of your comb will pass through the cavity in exactly the same way, enhancing your system in this build-up cavity. And here are some initial papers on optical frequency comb spectroscopy and cavity enhancement. But then you might say, well, why can't we take this all the way? If we have our Nisomes ideas and we now have this optical frequency comb, which we want to cavity enhance, we could put it all together. And this is exactly what's been done. So you not only have your free spectral range and your repetition rate of your comb lined up, you produce side bands on every comb line. And then you can do this demodulation of the detection signal and gives you the same noise immunity as in your original Nisome system. But instead of just at a single frequency measuring a single molecule, you can now have an entire span of molecules that you can detect simultaneously. And again, these are all kind of real-time detection methods. It's not something you have to integrate for hours or days. So I'm sure I've come to the end of my time here. So just to summarize, the kind of requirements we were looking for had to do with selectivity, sensitivity, speed, and how you could calibrate the system. And I think in the optical sensing methods I described, they're very molecule specific. We currently like small, simple molecules, but there are other detection methods that are very powerful for the more complicated ones. It's ultra sensitive, easily looking at parts per trillion and less for detection. As these things are developed, it's definitely a real-time, less than a second online measurement technique, and it can be calibrated to primary gas standards or directly to optical frequencies so that you know exactly where you're at. What we need to look further in is on these kind of more cutting-edge optical frequency combs and microcomb techniques is looking into multi-species detection with a single device and extending into the mid-IR, which for microcombs is absolutely possible. It just depends on the material that you create, that you fabricate your microcomb out of. So that completes my talk. I'd like to just thank my coworkers in the NPL Time and Frequency Department and other collaborators at NPL on this work. We're funded by a number of European collaborative ventures as well as by BASE in the UK. And if you would like more information, please feel free to contact me directly. Thank you.
Thanks, Anne. I have some comments, but maybe it would be good if there would be first some other questions from the audience. Do we have anyone?
Yes, from Thomas. Hi, Anne.
Hi.
Eplana sells some lasers to you, and we have some narrow diamond lasers. So do you have some kind of application for that for gas sensing? Like we have these special lasers that are having this narrow line width. So is it better to couple to the cavity than a normal laser like a QCL or?
Yeah, absolutely. One of the big challenges in going into the mid-IR is the narrowness of your laser sources. Though I've read that you can absolutely stabilize QCLs at the kind of sub 10 hertz level. So obviously it's possible. But we're looking for kind of off-the-shelf lasers with a megahertz or less free running line width. And we have definitely bought some lasers from your company that fit the bill for some detection in different regimes. So it's really about finding a laser, preferably one that's fiber coupled, because that makes the system much more robust and simple to put together. It needs to have we found that to get the narrow line width, the lasers really need to have internal isolators to isolate
Insulator, sure. Yeah,
feedback. And
sure,
that's the difficulty if you're trying to get individual lasers at every wavelength in the near IR that you'd like to for gas detection. Is there seem to be only very specific lasers, usually ones that are currently being used for gas detection, whether it's ammonia or water or CO2 at 2 microns, you can find them. But yeah, that's one of the key important things if we really want to be using these high finesse cavities, is to start with as narrow a line width laser as possible.
sure. Thank you.
Okay, do we have other questions? Yeah, maybe I would then just like to comment. I think these are maybe for, let's say, people not that involved in optical or laser-based spectroscopy. This is the that I would consider the high end, definitely. And well, one might then argue that okay, this seems way too complicated. So this I mean, you cannot transfer, you cannot package this and make it stable and transfer it into a field use. But when was it?
Well, wait, I
Also.
did stop you there because I think you can, but
Yeah,
yes,
yeah.
I
But
do
I mean,
agree it's much more complicated.
I'm coming there. So I mean, for example, I think the first cavity ring down, let's say, systems or the concepts were demonstrated around 30 years ago,
Mhm.
and they have been on the market now for, I don't know, 10, 15 years. Maybe Graham knows better, but still for a long time. And now there's definitely there's been a push to combine these frequency comps with cavities that would kind of unlock, let's say, a multi-species detection potential, sensitive
Mhm.
detection potential, but by optical means, and also pushing the kind of the detection wavelength from those weak transitions in the near infrared to mid infrared. That would mean or translate into higher or better sensitivity. So I mean, this is it's definitely still uh, some of this is research grade or level, but I would expect that something will definitely come up in the next, I don't know, 5 years, 5 to 10 years.
Yeah, I would say
And
the kind of Nisomes level systems you could imagine miniaturizing and ruggedizing and having multiple species detection in some niche where another
mm,
device can do most of the job but can't do HCl or ammonia very well. And so here's the device you just stick in with it on some larger scale measurement system. But in terms of
yes,
the optical frequency combs, you could buy one and use it
yes,
with
that's true.
not. I mean, they're almost turnkey systems that are
Yes,
being developed, but they're expensive, and I think they take
that's
some
true.
skill to run. But
Of
these
course.
microcombs, that's maybe a 5 to 10 year time horizon before you've got something you could really just integrate into a system, put a cavity around it yourself, use it for
Yeah,
spectroscopy. But I mean that's to me the holy grail of
yeah,
using optical systems to do detection, because it covers everything you're looking for. You just have to model things very well so that you know what lines you're looking at.
of
But
course.
it's quite simple in
Yeah.
how you'd calibrate it. And yeah, no, I think that's really the exciting frontier.
Yeah, that's kind of the, let's say, one of the big promises. That maybe time will tell when it's. I think it's about when and not if when it will
Mhm.
happen. But maybe, I mean, time will tell. Uh, if we do not have any other questions or comments, maybe we should move on and start kind of our final session titled Generating, Sampling, and Handling of Airborne Chemical Contaminants. And the first presentation is from Michael from NPL, so you can use the same